Okay, welcome to the next talk in the session. It's by Stephen Murdoch. He's a researcher at the University of Cambridge and also in the OpenNet initiative. And today he's going to present something about detecting temperature through clock skew. And he's doing something which normally medical doctors are doing, like measuring temperature. Okay, welcome.
Okay, hello everyone. So, this is a summary of my talk. Once it comes on the slide. Yep. So, I'm going to talk about clock skew and how it's going to find security vulnerabilities in some systems. So, firstly, I'm going to give some background on what clock skew is and also how it's affected by temperature. And because I'm interested in looking at it over the internet, I'm going to show how to measure clock skew remotely. I'm going to illustrate how this affects Tor, so I'll give some background on how Tor, and in particular how Tor hidden services work. And then I'm going to detail the attack. And finally, I'm going to conclude with a few other ways that it might be possible to use clock skew to do interesting things. So, firstly, for the purposes of this talk, I'm not talking about only real-time clocks that represent the time that you'd find on a watch. A clock is anything which measures a period of time. So the first part of this is an oscillator, and that's controlled by a clock crystal. And this ticks at a certain predetermined rate. And this feeds into a counter, which counts the number of ticks and makes that available to something else. Sometimes this is a special purpose device, but in the examples I'm looking at, this is all controlled by the CPU of a computer. A computer will generally have multiple clocks, and I'm going to talk about a few of them here. I'm going to give examples from Linux, but other operating systems are quite similar. The one important clock is the Jiffy counter, and on Linux this is only available to the kernel. Importantly, it's not corrected for any clock skew, and NTP doesn't apply for this. There's also the system clock, which is the one that is actually available to the user mode programs through the get time of day system call. It's also corrected for NTP, which makes measuring the clock skew of the underlying clock crystal a bit harder, but still possible. But this shouldn't be confused with the BIOS clock, which it runs even when the computer is off, and it sets the system clock once the computer is booted. On older computers, this was a dedicated chip, often made by Dallas, you might see it. On more modern computers, this is integrated with the chipset, like this picture here. So I mentioned that I need to measure clock skew remotely. This means I need to somehow get timestamps from a computer. And there's a few ways to do it. One of the most obvious ways is the ICMP timestamp request. This is a packet where you send it to a computer and it will respond with its notion of the system clock. One advantage is it's comparatively fast. It runs at 1 kilohertz, and it's from the system clock, so NTP synchronized, which is a bit of a problem for what I'm doing, as you'll see later. Another disadvantage is that on the open internet, ICMP is commonly blocked unless it's known to be a useful thing. And in this case, ICMP timestamps is not essential. So if it's on at all on a host, it might be blocked at the firewall. Another one, which actually brought me onto this topic, I talked about at the last Congress, which is on Linux. You can estimate a notion of a computer's time by the TCP sequence number. This is because when a sequence number is generated, the host will take the source, destination, port and IP address, hash them all together, and then add on a 1 megahertz clock. So that's good because it's very fast and that allows you to estimate the time very accurately. But it's from the system clock, so it's NTP synchronized, which is a problem But one thing on the good side is it's actually very hard to block on firewalls, because if you block initial sequence numbers, then nothing works. And if you want to know more about this, there's some more information in my previous talk. The slides are on my website. But for the rest of this talk, I'm mainly going to talk about the TCP timestamp feature. This is a fairly new feature, but it's enabled on all modern operating systems that you find now. The specification doesn't say which speed the clock should be. In practice, it varies between 2 Hz and 1 kHz. On Linux, it goes between, I think, 100 kHz and 100 Hz and 1 kHz. It's generated from the Jiffy counter, and this is good because it's not NTP synchronized. And it's also quite hard to block on the firewall because it's a TCP option, and firewalls will typically not manipulate packets. On very fast networks, it's actually essential to have the TCP timestamp, otherwise the sequence number will wrap around and you can get losses of data. It also increases performance. So, some more terminology. Offset is the difference between 2 clocks. So if my watch says it's 12:51 and your watch says it's 12:52, then we've got a difference of 1 minute, and that's the offset. For the rest of the talk, I'm going to measure this in milliseconds. But if my watch has an offset of 1 minute today and 2 minutes tomorrow, then there's clock skew. There's 1 minute per day. This is when the speed of the clock is wrong rather than just the phase of it. This is commonly measured in parts per million, and for, as an example, 1 part per million corresponds to 1 minute every 2 years. So this graph shows 6 computers and their offset over time. Each of these dots is one TCP timestamp request, and trying to estimate the offset from that. There's noise, as you can see, but if you've tried to fit a line over the top, it pretty much matches the points underneath. And the slope of this line is the clock skew. So there was a previous paper in 2005 by Yoshi Kono, which showed that clock skew of a host acts as a reasonable fingerprint. That's because it doesn't change very much over time on one computer, just 1 or 2 parts per million, but different computers, even from the exact same model, will have a significantly different clock skew, up to 50 parts per million. And this allows you to get 4 to 6 bits of information on a host. So it's not, by no means, completely unique for all computers, but it can give you a reasonable idea. So this has a number of consequences. Firstly, you can identify machines as they move. If you're using your laptop here and then you want to be untraceable, so you take it someone else, even if you've got a different IP address, different location, the clock skew will be largely the same. In network research, it's common to release network traces for measuring properties of TCP and various performance measurements. For privacy reasons, IP addresses and other information that could compromise people's identity is removed. But clock skew remains. So that paper showed how you can use clock skew to de-anonymize such network traces. Virtual machines have a very different clock skew pattern from physical machines. So if you have access to an IP address, you can use clock skew to find out whether it's running on a virtual machine or whether it's a physical one. And similarly, you can find out whether you have multiple virtual machines on the same physical host, because they'll have strange characteristics because it's a virtual machine, but it will be the same across all the virtual machines. So some of you might have heard of HoneyNet, or the HoneyNet project, and HoneyD is one tool for using this. And this has now been modified so that each virtual host will be given a random clock skew. You can also use it for counting number of hosts behind the NAT. If you see all the packets coming from this box with the same IP address, it looks like they're all the same host. But if you look at the clock skew, then you might be able to see that there's a few machines behind this. This can be useful for trying to do network mapping if there are some other restrictions. But although in the extended version of the paper they did mention temperature, they didn't really go any further and didn't do any experiments on that. So that's where my talk is going to start off in the new material. This graph on the right-hand side is from a datasheet for a fairly typical clock crystal for a PC. On the vertical axis, you have the clock skew, and the horizontal axis is the temperature. This is over the full operational range of this particular clock crystal, which is minus 50 Celsius to 100. But within a PC, things like the hard disk are going to fail well within that area. So in practice, a PC, although not the CPU, will spend most of its time in this tiny box here. So let's look a bit more closely there. So in one of my tests, I saw that a temperature changed between these 2 points, about 2 degrees Celsius, and there was a corresponding change in clock skew. And that's more or less consistent with what the data sheets say. And this is quite a small difference in temperature, and it's affected by the outside world. So even in the Cambridge Computer Lab, which is a very well insulated building, you can still see the change in temperature over a day. So in order to find out the clock skew of a host, you need to do some analysis of the raw data, because as you can see, it's actually quite messy. So this is probably the important section of my talk. If you understand this slide, then you understand the rest of it. I'm going to describe how to go from the raw network data into a clock skew measurement. So firstly, I measure the offset. These are all these grey dots, and try to fit a line over the top of them. And you can see that I've got these for each of these hosts. Now, the points match this line quite closely, which means that the clock skew is constant, which is not what I want to see. I want to see changes in the clock skew. And this is because the absolute clock skew, how it varies between hosts, is very large compared to how the clock skew varies. So if I subtract this diagonal line and shift all the points up, then I get something like this. I'm now going over a much longer time period, so I can see more data. And you can see that there's noise. This is from 2 sources. Firstly, there's network latency between a packet being sent out and when I receive it. There's a certain amount of time, and this varies. Also, there is quantization noise. I mentioned about different clock speeds. This means when I sample a clock, I might be sampling just before a tick, or just after a tick, or a long time after a tick. And this introduces noise as well. And that's why it's almost exactly 1 millisecond, which corresponds to a 1 kilohertz clock. So, as before, I try to remove this noise by drawing a line over the top. This time, it should be a curve, but it's much simpler to take a number of segments and overlap them. So there's one, and there's another one. And in order to actually find out what the skew is, it's the slope of this line. So if I differentiate it, I get this kind of graph. So as you can see, it's a little bit noisy, but there's something clearly going on around about 8 o'clock in the morning on Saturday. And this is approximately when the air conditioning in the computer lab gets turned on. It certainly isn't, because I'm in the lab at 8 o'clock in the morning on Saturday. If we compare this to temperature, there's actually a reasonable match. So this justifies that maybe this is actually going to work. But how can this be used for more security purposes? Tor is an anonymity network. If you want to browse websites anonymously, then this is a reasonable way to do it. It works by going through a random selection of volunteer nodes. When you want to go to a web server, you first of all look up